Dr. Khemchandani has finished a PhD from IIT Delhi in 2008. She has been with the Royal Bank of Scotland as a senior VP for several years. She has published a good number of research papers. Currently, she published a paper in Annals of Optimization. Then one of their work is very monumental in the sense that twin support vector machine SBM has been extended with the SBM and got about 500 citations or so. She has already published 20 odd very good research papers and around 500 citations in total. She has joined our university last year and we hope you will be enjoying her lectures.
Because there's a problem with your character. I'm audible to the last row? Yes, right? So, you better do switch off that. So, thanks for the introduction. Today I'm going to explain you support vector machines. I hope you have enjoyed a lot of classification testing techniques so far. This is one of, another technique for classification from a support vector machine. So what's the difference between the algorithm which you have discussed or learned so far and support vector machines? The basic difference which I could say is the earlier one is parametric and this is non-parametric approach. So you won't require all these stuff, how many k should be there, what is the density for the data, are we assuming any mean, standard deviation, nothing is there. No prior probability, no posterior probability, nothing is there. So you just need to have a data, right? And then what we are learning here is a classifier. So classifier which would be a hyperplane. So we have already seen that in a two-dimensional data, you have suppose presented by a height and weight. Like in the previous day we have an example of Punjabi versus Bengali, right? Punjabi versus Bengali. So in that case also, you just need a classifier. Put the features in that and find out whether the person is Bengali or the person is Punjabi. So let's start with the presentation. So I will start with an introduction of support vector machines, its properties and its application. I couldn't cover much, so one is for the cancelled classification and the other is text categorization. I'm so sorry, I pressed the wrong switch. So let's see. So let's say we have two classes here, one represented by these black dots and other represented by these white dots. Now I would like to know a classifier which would differentiate between these two classes. So how would I do that? Right, I have a representation in 2D. So if I could get hold of a classifier, something like this, which could differentiate between the two classes. So just I need one hyperplane. And this hyperplane knowledge would be driven with the help of these data set. Once the hyperplane is there, I need not have all the information of the data. So let's say if I am working with a 1 million data, I don't require 1 million data information after I have built up this classifier. Now what is meaningful to me, whether the test pattern, the new pattern which I have, will be classified correctly or wrongly. That's the only motive to have. So that means there are two things to have. One is, once you have a data, you need to have a training and to have a testing. Right? Training is something by looking to the data, by looking to the class tables, what would be the classifier. Once you have the classifier, then what would be the test set accuracy. So generally what we do is what we call as 10-fold cross-validation, right? Where there we have a data set, we divide into 10 subsets, 9 of them is used for training, right? And the 10th is kept as for testing. So you have the testing classification accuracy. Once you are satisfied with that, you restrict that classifier and then you use it for the further purposes. For example, if I would like to know, apple versus oranges, what will I do? I will have the features of apple and I have the features of orange, right? And then I will build a classifier like this. Now, if the new fruit comes in and if it has a characteristic similar to that of an apple and an orange, then I would classify into that. But let's say if grapes comes in, then with that particular feature, I and then it will give me a wrong classification to that grades, right? So let's see how this maths go on. So the idea is we can take this as a black box, although we have a proper optimization tool sitting inside which gives us this classifier. But let's say we have a black box, this F, right? And this is basically the data goes into this black box, it gives me a classifier and hence the class grade. So when we say a hyperplane, what does it mean? Like let's say in this two-dimensional we have 2 points. One is 2, 0, another is 0, 3. Everybody of us, we know how to find out the equation of a line, right? So that is what we are calling the hyperplane in 2D, right? So we have a classifier like this. Now the point is that is this the true classifier or is this a classifier which I am looking at? Because by just looking at the data, this is one hyperplane which could differentiate between the two classes. But is this optimal? Because I can have various others. Like this is also classified, right? So many of them. So I should have some criteria, some optimizing rule or some optimization problem which could give me optimal classifier. Now the point is, when we say optimal classifier, what does it mean? This means that, see, initially I told you that we are going to have a cleaning accuracy as well as testing accuracy. So we would like to have good cleaning accuracy as well as the testing accuracy. By cleaning accuracy, in the previous lectures also you have listened about the two terms. One is the learning of the data, the other is the generalization ability. How good it performs on the unseen data, right? That is what we call testing accuracy. So that means I would like to have both in my optimization problem so that the classifier which I get would give me a best testing accuracy, a best generalization ability, right? Because as I said, I am going to throw away the training data once I have built up with this classifier. Now, the other reason is, let's say I have built up this as a classifier. Now, this point, right, which is close to this cluster, if you say that, right, or to this class, then it's going to wrongly classify this to this class. That means this hyperplane is not going to give the correct classification to this pattern, right? So that means this is misclassified point, and if I take this as the classifier, then the problem will come to this particular point, right? This particular point would be, or let's say a point which is going to lie in this particular region, the ambiguity will still remain. So that means a hyperplane, a single hyperplane won't be a sufficient thing to have here. What we need, something is called margin. Now, before coming to the margin, we need to have few terms. One is a dead zone. Now, a dead zone is a region where no pattern lies, right? Where no pattern lies, that means from both the classes, I would like to have a zone where no patterns from either of the classes should lie. So, and a margin, what we do is, we find out the dead zone. Like in this case, let's say this is my dead zone, right? In this there is no pattern which is lying from both the classes. So what will I do? I will, and this is my classifier. Classifier would be a hyperplane between the two. Now, this is a parallel hyperplanes, right? This is what we call as the bounding hyperplanes. And the region between these two is what we call as margin. So this is a dead zone where no patterns of either the two classes will lie, and a margin would be this distance, which is the distance between the two parallel hyperplanes. And then a new term which I am starting from beginning was support vector machines. Why we are calling this support vector machines? That means these bounding planes would have to do something with the support, right? So that means those patterns which are lying on this hyperplanes, right? In this case, these three points, they are the support of this hyperplane or the classifier. So we call them as support vector, and hence a term coined in which is called support vector machines, right? So far what we have learned is that we are going to create a dead zone, a parallel hyperplanes, a distance between them which is the margin, and we would like to have an optimization problem which is going to maximize this margin. Because more the margin, right, better the generalization ability, right? Because you have a zone where no pattern lies while you are doing the training. So you are expecting the test patterns, which are unseen patterns coming from the same distribution, right? Because it is obvious that if you have made a classifier of let's say an apple and an orange, you won't expect a banana to come in or a grape to come, right? Or if you're working with a human being, you won't consider an animal to come in and you're going to test that pattern. So patterns have to come from the same distribution, right? So in this case, what is margin? The margin is, as I said, this is between the two parallel hyperplanes, right? And this is turns out to be equal to 2 upon norm W. Norm W in this case is the Euclidean distance norm, right? L2 norm. So the norm W will be represented by, so if we are working in 2 dimension, it will be W1 square plus W2 square under root of that, right? So that's fine. So what we have made so far the objective function, which is to maximize the margin. Now the constraints. You would like to have the classes to be correctly classified with the help of these parallel hyperplanes, right? So what you would like to have, since the supervised learning, so you have the class label beforehand. So the patterns for which you have the class label as 1, you would like that it should lie on this side of the hyperplane, right? So W transpose X plus B should be greater than 1. And those patterns which are on the other side of the hyperplane should lie below this hyperplane. So you have W transpose X plus B less than equal to 1 for those which you have the class label as -1. So that means in total you would have this constraint as yi W transpose Xi plus B less than equal to 1. Now we have the constraint, we have the objective function. That means an optimization problem is ready for us to optimize, right? So this is what the optimization problem will look like. We would like to maximize the margin, which is same as minimizing norm W upon 2. Are you aware of quadratic programming problem? You know what is quadratic programming problem? Anyone? Yes? So in this, basically this turns out to be a quadratic programming problem where you are minimizing the margin subject to this particular constraints. Now imagine a scenario where you have 1 million constraints to deal with, right? You have 1 million pattern to deal with. Nowadays we are talking about big data, right? So that means that the number of constraints is going to be 1 million, trillion and so on. And if you are working in the financial data, right, then the data set is huge because you are recording entry at every microsecond. And if in a day or a week data, the data set is going to be very large. So in that, if I am going to solve this problem, this will have 1 million constraints, right? Very difficult to solve. Very difficult to solve. So that means we need a way out of it, right? So what would be the way out? It would be something like you solve the dual problem, right? Because the advantage in this case is when you solve the dual problem, the number of variables will turn out to the number of constraints, and the number of constraints would turn out to be the number of variables. So if I have 1 million constraints in my primary problem, the dual problem will have 1 million variables, right? And in this case, the beauty is that after getting hold of the dual problem, we just land up to just one equality constraint, right? And that's it. So this problem is again a quadratic programming problem, a convex optimization problem, where you have an optimal solution. So the beauty is you have an optimal solution. There is no iterativeness in this case. If you have a solution, it will be unique and global, right? So for writing, the dual problem, you need to get hold of all these KDT conditions. So if the problem is of the type minimization of fx subject to the constraints greater than equal to 0, gix greater than equal to 0 and hix equals to 0. So the necessary condition to find out the dual problem is what we call as the KDT conditions, and the solutions are obtained like this. So this is something if you are interested in, then probably you can go through all these details. But the point is that in this case, we landed to again a convex optimization problem. See, all these are details. Let's skip that. Now, as I said that there is a primal variable W, so we are looking to W transpose X plus B. So this is a variable W and B are the variables, right? So this is in the dimension of X. Let's say you are dealing X in Rn. If you want, I can take the number. Let's say in R10. So your W will also be in R10 and B is a real number, right? So we are not solving the primal problem, right? We are solving the dual problem. So obviously we would like to have some relationship of primal and dual so that we can get hold of the classifier, right? So from the KKT condition, what we get is that your W is nothing but a linear combination of alpha I, yi and xi. Now you need to concentrate on this point. See, when we say alpha I, yi and xi, see W is nothing but a linear combination of alpha I, yi and xi. So those alpha i's which are non-zero, right? Because remember, I said when we are dealing with the primal problem, it's a 1 million constraint. You are not dealing with the 1 million constraint, but you are taking the dual problem where you have 1 million variables. Not all variables will have a non-zero value, right? So let's say out of 1 million, you have just 100 of them to be non-zero, right? So what will happen? That the solution, only 100 such alpha i's will contribute to your solution. That means in this summation is running over all those points for which you have alpha I non-zero, and those points for which we have non-zero alpha i's, we call them as support vectors. So if you remember that diagram, which, let me go back. In this diagram, so these 3 points are basically the support vectors. Support vectors, so that means if I am going to solve this problem, right, I will have only 3 alpha i's which are non-zero. Apart from that, every alpha I will be 0. So I need to just get hold of these 3 alpha i's. I need just to remember these 3 alpha i's. So see the sparseness of this, hyperplane construction or the classifier. So with that, so the solution has this particular form, and once you have the solution, you just put in this value of W in this classifier, and then you would like to see the sign of this. So if this is greater than 0, we will say it belongs to class 1. If it is less than 0, we will say it belongs to class -1. Any questions so far? Fine. That means now so far we have considered a linear separable data, right? So as I said, if this problem will have a solution, it will be unique. When I say if this problem has a solution, that means the underlying assumption which I am going to make here, that there is no error or the data set is linearly separable. I could find a hyperplane, such that I am going to get hold of this classifier, right? But in general, the data set is not like that, right? In general, the data set is where you have this type of noise, or you can say the data set is like that. In that case, if I am going to solve that particular problem, I am unable to get hold of a solution. The problem will say no solution exists. What is the solution then? In that case, shall I say that support vector is not going to work? The answer is no. What we can do in this case is, we could try, I was working with a linear kernel, a linear hyperplane, a hyperplane W transpose X plus B equals to 0. But I could go to a higher dimensional space where this data set is linearly separable. That's one. The other is, I can have a compromise on this particular points, and I say get rid of these points, get rid of these points and find out a classifier. But in a 2D data, I can see which are these points and which points I can get rid of. But in general, data set is not like that, right? You have a multidimensional data, you cannot even have a visualization of that data. In that case, what will I do? That means I need to incorporate such a component in my optimization problem, which would give me that these are the points which has certain error, and if you compromise on these error, you would get hold of a linear classifier, right? I just skip this slide. This is basically with some optimization problem where you have all these patterns, and this is just to show that the points which are lying on the bounding plane, you have the corresponding Lagrange variable non-zero values, and these are going to contribute to your decision surface. So, as I said, I can have this nonlinear kernel also, but that would result in an overfitting. So, the other way is to introduce an error to this particular points. So, let's say this pattern, right? This pattern, because I said we are going to have a dead zone, a zone free of the patterns. So, since these patterns are lying inside this zone, so we will say that actually we have the error component, error variable for all these points. Sorry. But when you solve this optimization problem, for these particular points, you will have non-zero error. And for all these points, you will have the zero error. So I have designed, Pavlik has designed this problem, and finally it turns out that after you solve this optimization problem, those erroneous patterns would be patterns which are lying in the dead zone. So as I said, we are going to introduce this component in the objective function. So my objective was to maximize the generalization ability, that is to maximize the margin. Along with that, I would like to minimize this empirical error. So this is basically the training error, total training errors, right? So this is again an optimization problem. So there is a small difference between the one which I discussed earlier, which we called as hard margin classifier. This is something we are relaxing the classifier to incorporate these errors, but with the linear classifier. So the only term which gets added here is this total error subject to the same constraints, right? This xi I is basically the erroneous variable. Now, if if the pattern is going to commit an error, you will have a non-zero value for the xi I. Otherwise, this variable is going to take a zero value. Now, the point is, this says generalization ability, and this says training error, right? So we can say this is a testing error and this is a training error. So we have a compromise between a training error and a testing error. So you could have a data set where you have 100% training classification accuracy, but very poor testing accuracy, right? That is the case you have done overfitting, right? So to avoid that, what we do is generally we take this C as a user defined. So again to analyze this value of C, let's say we have cancer data set, right? Now in the cancer data set, I cannot manage to have a single error, right? Why? Because the data set there itself has only few patterns. Let's say I went to a hospital and from there I collected the cancer data set, the patients for which I have a history. So among, let's say, 100 patterns, 100 such patients, I could get hold of 20 patients who have reported cancer in that particular hospital, right? Now I have those features. Now I want my classifier to correctly classify those patients which have cancer. Like for example, if the doctor comes to me and says, okay, could you please build a classifier for us which could help me in classifying the patient to be a cancer patient or a non-cancer patient, right? In that case, those 20 patterns of the cancer patients are very important to me, right? I cannot bear to have a single error in that case. So in that situation, this C will take a very large value. I cannot have a 0% error in this case, so my training error should be as good as possible. right? In that case, C should be very large. But like for example, if I am dealing with a 1 million data set, which is representing, let's say the cars which are breaking the traffic rules, so I can manage to have an error in that situation. So this C value would be very low in that particular case. So depending upon the situation to situation, you are going to fix up the C value. Now again, similar to the optimization problem in case of hard margin classifier, we have an optimization for the soft margin classifier, and this is the corresponding dual problem. The only difference, if you could notice, from the hard margin and soft margin classifier is the bound on this Lagrange multiplier. Previously, the only constraint on the Lagrange multiplier was that it can take the value greater than or equal to 0, right? Now we are bounding above by that variable to the C, and now C is a user defined, as I said. So in the case where C is going to take a very large value, alpha is free to take as large as possible, and where C is going to take a very small value, let's say 0.1, then alpha is going to bound between 0 and 0.1, right? So this is an overview. So far we have discussed a linear classifier, right? So we are discussing a hyperplane form of a classifier, W transpose X plus B equal to 0, and we get hold of a sparseness property because we have seen that those alpha i's which are non-zero are going to contribute to the hyperplane equation. Remember, so those are support vectors. Then it's a quadratic optimization problem. The solution exists. It will be unique. It will be optimal. Right? No iterations is required. And once you get hold of these alpha i's, you can decide upon the class of a new pattern by just substituting in this equation. If it is greater than 0, it belongs to class 1, else it belongs to class -1. So far so good, right? We could manage with linear classifier. Now let's imagine a situation where linear classifier won't work, right? Like for example, in this case, let's see in this case where this class cannot be separated from these class by no matter whether you take any. So in that case, you need to have combination of two classifiers, right? One from this side, another from this side. A single classifier won't work. Then in this situation, what we will do? We will project them to a higher dimension space like this. So I have taken a polynomial kernel, right? So I have increased the dimension from 1D to 2D, and with that, we could get hold of a linear classifier in a higher dimension space. So if I am unable to get hold of a linear classifier in a lower dimension, I am projecting into a higher dimension and get hold of a linear classifier there. Now what is the problem here? How do I know which mapping should I take here? Whether I should take polynomial, whether should I take Gaussian, right? Or any other sigmoid kernel, or 10 kernel, or whatever the kernels are. There are so many kernels. I will discuss them in my slides. But which should I take in this case? So that's a one open question here. But before that, let's get comfortable with this. Let's say we have these three data points, 0, 1 and 2. So if I am going to take this polynomial kernel, these points 0 will map to 0, 0, 1, 1 map to 1, root 2, 1, 2 maps to 4, 2, root 2, 2, root 2 and 1, and with that it becomes linearly separate. Right? So the idea is that you project your data to a higher dimension space where this becomes linearly separate. Right? Now, if you, I just go back to this particular slide where we had this dual problem. Now, if you see, you have an inner product of xi transpose xj. I can write this as xi comma xj, inner product of xi comma xj. So that means if I could get hold of an inner product information, right, then I may not need the kernel, I may not need the mapping, right? Why? Because see, in this case, when I did this pi mapping, right, I projected this pattern to a high dimension space to get hold of the representation. But this is something which I don't require when I am solving the dual problem. Why? Because there I am using an inner product between the two patterns. So what information I require is what is the inner product between these two patterns, right? What is the inner product between these two patterns, and indirectly what is the inner product between these two patterns? That's it. That's the information I require. So that is why I come to the question. But I said this is one of the own problems, which mapping to select, right? But I will come to a question. But before that, I'm going to get rid of this mapping business. Why? Because, as I said, I'm going to concentrate on the inner product, right? So, inner product means, so instead of this phi xi and phi xj information individually, I am looking to phi xi transpose phi xj. This information I am looking at. Now, this is equivalent to an ij entry of a matrix. If I see, I have, if you, let's say we have x10 patterns, right? So this is nothing but phi of x1 transpose phi of x1, phi of x1 transpose phi of x2, and so on. Phi of x1 transpose phi of x10, and similarly I can build up this matrix. So this is nothing but some entries in a matrix, let's say K, right? So that means finally I am not interested in this individual mapping, but I am interested in this entries of the matrix K. And where this is coming in? This is coming in the optimization problem, right? And this is a convex optimization problem. So what I need is that this objective function, right, should be positive definite, semi-positive definite, right? So any matrix, any K matrix which is a semi-positive matrix, I can take that and put it here and do the classification job, right? So that means the knowledge of a mapping is there, but implicit calculation of this mapping is not, right? Because ultimately I am leading to a calculation of something like this, 1 plus xi transpose xj square. I know that I am going to use a polynomial kernel, but when I do so, I end up to an inner product of these two, right? And there I get hold of this K matrix, and the only requirement which I need is that this should be semi-positive definite matrix. And these are the few kernels, right? So now there is only one thing. You have seen the Alice data, right? In the Alice data, we have seen one class is linearly separable from the remaining two classes, right? Now, if I use a linear kernel, right, what will happen? Now, first of all, this is a multi-category data set, right? This has 3 classes. But let's say if I am going to take it as let's say we have one representation of iris as this. So in this case, this class, let's say this is 1, this is 2 and 3. As if this is a multi-category data set, I will also discuss how to deal with the multi-category classification. But let's say if we club 2 and 3 class together and 1, so I am doing 1 versus 2 and 3, right? In this case, this is linearly separable. So I know a linear kernel is going to work in this case. But if I want to separate, let's say 2 versus 3, 2 versus 1 and 3, right? A linear kernel is not going to work here. I cannot define a kernel like this, a separator like this, which is going to separate because these points will get wrongly classified, right? So in that case, we need to have another kernel. That is, the next would be either the polynomial kernel of degree 2 or an RBF kernel. So an RBF kernel would give me a classifier something like this, right? Which would classify my class 2 correctly, but would have a small misclassification of class 3. But the distribution of this would be very low as compared to because each class has 50 samples, right? Each class has 50 samples, so these points would be very few, so I can manage with those errors. right? So that is the scenario. So how to decide upon the kernel? Again, I will discuss. There is something called validation set, right? So you, what you do is, as the sir also said, in the clustering algorithm, you do a subspace clustering, right? So you come back to a smaller dimension and then try to get hold of the picture of the data, and then you see which distance is going to work there, which distance median is going to work there. So in this case also, what we will do is we take the 10% of the data set, right? Randomly selected 10% of the data set, and in that data set, we do this checking whether you are going to use linear kernel, whether you are going to use polynomial, or whether you are going to use RDF kernel. Depending upon the choice of the kernel, which kernel gives us the best accuracy, we take this 10% data set back to the whole data set and do the classification job there, right? So this is how we select upon the kernel. So again, the only difference comes here, you introduce a mapping, matrix or the matrix K here and do this optimization. So let's just overview the nonlinear SPMs. This also locates a separating hyperplane in a feature space and classify the point in that space. It does not need to represent the space explicitly, simply by defining a kernel function will do, and a kernel function plays the crucial role, and it is defined in the form of an n upper down. Now, properties of SPM. Now, if you see, in this case also, when we say inner product between xi and xj, what we are looking at basically similarity between the 2 points, right? Similarity between the 2 points. And when we say we are projecting it onto a higher dimension space, there also we are basically looking to the similarity of the samples. So since it is supervised learning, you know which samples belong to class 1, which samples belong to class -1. So there you get hold of some sort of a similarity measure there, right? So the other advantage is sparseness, as I said, only alphas which are non-zero going to contribute to a solution. Ability to handle large feature space. Now, see, suppose if you are working with, let's say 1000 dimension, and when you try to solve this optimization problem, for those features for which the value of W is very low, we can consider them as redundant features. We can throw out those features, and with the remaining WIs, because what this says, when you say you are going to have a W transpose X plus B equal to 0 as a classifier, what you are doing is basically you are trying to give it weightage to all those features, right? Let's say you have n features. So in an optimization problem, if this has a very small value, that effectively tells you that this feature is contributing in a small percentage to the whole classifier. So I can get rid of that particular feature and work with those features for which my WI is comparatively larger than the remaining ones, right? So this can also be used as dimension reduction problem. And now with the remaining WI, the remaining exercise, you can rework the classification job and you can build up the classifier. The general model selection procedure, what we do is cross-validation and leave one out. Now, where to use cross-validation and where to use leave one out? As I explained, when we are dealing with data set like cancer classification, where each such pattern is very important, or like for example in a DNA classification, where each such DNA contribution is very important, we will do leave one out cross-validation as well. So we will check whether every such pattern has got its correct classification or not. Otherwise, we generally do 10-fold cross-validation, 5-fold cross-validation, it's one and the same thing, or we can call this as K-fold cross-validation, where we try to make K subsets. So given the whole data set, right, we divide it into K subsets. K-1 we take for training, K for testing. Repeat this K times and report the mean and standard deviation. That is generally we all do when we report some new algorithm and then try to compare it with the other existing algorithm. We generally report mean plus standard deviation. So let's summarize. We are trying to have a data matrix, right? So data matrix is you all know. We try to figure out which kernel to use. We select the parameters C, execute the training algorithm, find out the value of alpha I, and then try to find out the classifier. Now see, when we say big data, right? So there the task is to classify, let's say, 1 million points. Since we know this sparseness property of SPM, what we can do is we can bring the data in a batch form, or we can realize this that the data is coming online, right? So once you have made up the classifier, as I said, while training you need all the patterns, but once the training has been done, once you have made up the classifier, you can throw over the training patterns, right? So what I can do if I am, let's say, working with 1000 data, right? And the next 1000 is going to come in the next chunk. And then the next on, let's say, a day 1 data of financial domain I am working with. Now for the day 2, when the next data comes in, I know my classifier for day 1. I know what are my support vectors. I will retain those support vectors, take the new patterns, next 1000 patterns, find out my classifier, and then just take those patterns which are the support vectors, right? And then move this further. So that means I can use this when I have a 1 million data set, right? I can make it a batch form. I know I cannot handle 1 million data set. It's not you solve the dual problem and get away from this problem. That's not possible, frankly speaking, because you need to store that data, right? So what you can do is take the data in the batch form and divide it 1 million data set into batches, and then get hold of the support vectors, and in that way you can do the classification for all 1 million patterns, right? So this is one. This is also called as incremental support vector machines. So there are various ways we can get hold of the support vectors, erroneous patterns. So there are various modifications to this problem. But we could do so because of the sparseness property of SPM. We know that not all patterns are going to contribute, only few patterns, only support vectors are going to contribute. But there are certain issues, as I said, the choice of kernel, the kernel parameters, and then which classification we should do, whether we go for hard margin, whether we go for soft margin. So again, the answer of all these questions lies with the validation set. As I said, 10% data set, do all these things, judge upon the criteria, judge upon the kernel, judge upon the kernel parameters, and take back the whole 10% data set to the whole data, and then find out the classifier. So there are various algorithms which are available online. You can use them. One of them is SMO, SPM-like, LibSPM, BSPM. There are several SPM classifiers which are available free online. You can use them. I just skipped this SMO part. This is just to fasten up the SPM process, because we are solving a quadratic programming problem. So what does SMO does? It takes 2 patterns at a time, and with the help of KKT condition, it gives you the solution very fast. So SPM has been applied successfully in many real-world problems: text categorization, image classification, bioinformatics, handwriting character recognition. So, but I am going to discuss only 2 problems here, maybe in 5 minutes of time. We do have, right?
Yes.
So, in the cancer classification, generally the data set is like that. We have few number of patterns, and again the dimension depends. Dimension is generally very large. So, P represents here the dimension, and N represents the number of patterns. And generally, the patterns are imbalanced. The example which I take for the cancer, there are only 20 patients out of those 1000 patients who are reported to be cancerous patients, right? So in that case, the class is generally unbalanced, right? So there is, in that case, how to decide upon, you remember the error function? So we have W transpose W plus the summation of xi I. So the xi I was the error variable, right? So we are trying to minimize this. So we are trying to minimize this error subject to those classification constraints. Now, in this case, what we are doing is we are giving equal weightage to all those error variables, right? But like in the cancer data set, we should give higher weightage to those patterns which are cancer patients and lower weight to those patterns which are non-cancer patients. So what we should do, we should replace it by C1 and C2, this with the cancer patient and this with the non-cancer patients. So this would be, so I would like to minimize a total error, right? So this has to be very large. Let's say put it this 1000. So if I am going to commit a one single error, this is going to shoot up my optimization value, right? So what will I do? I will make this as 1000, this is let's say 0.1. So in that situation, this will help me to give a classifier which is not biased towards the non-cancer patient, because the density is such, my hyperclean will deviate towards the non-cancer patients, right? Because there are only small points lying here and a big data set lying here, right? So my classifier would be bound to have a bias over and maybe wrongly classify this, or let's say this is sitting inside those patients, so I'm unable to classify. But if I give this higher weightage to them, then I may get better generalization ability in this case. So, but the only problem is that SVM is sensitive to noise, sensitive to outliers, sensitive to noise. SVM is sensitive. So what we generally do, what we do is, we have the data set, we know the class labels, we find out the mean and standard deviation. And those points which are away 3 standard deviations, we delete them. See that this is an erroneous patterns and this is an outliers. So basically I am considering those patterns for which are lying inside mean plus 3 standard deviations. So see, if we go with the normal distribution, this portion is very less, right? So mainly the data set comes under mean plus minus 3 standard deviations, right? So we generally avoid these patterns, right? This is one way to remove the outliers, to remove the noise, and then safely play with the SVM classifier, right? Feature selection I have already discussed with you. So as I said, the weakness of SVM is sensitive to noise, but we have a way out to deal with this noise. Now SVM is meant for binary classification, that it can deal with only 2 classification, 2 classes at a time. So how to extend it to a multi-category is very simple. What we generally do is, let's say we have class A, B and C. What we do is, we first make a classifier A versus B union C, then B versus C union A, and then C versus A union B, right? And then we know the decision rule. Decision rule says that either the point belongs to this or point belongs to this, point belongs to this or point belongs to this, and so on. Because you remember we have this W transpose X Fx as summation of W transpose X plus B. If this is greater than 0, we say that it belongs to class 1, and else it belongs to class minus 1. So in this case, the decision rule changes a bit. What you do is, you try to find out, so you have 3 classifiers here. Let's say W1 transpose X plus B1 equals to 0, W2 transpose X plus B2 equals to 0, W3 transpose X plus B3 equals to 0. What you generally do is, you try to find out the distance from all these 3 classifiers. Whichever is maximum, you say the point belongs to that particular. And there are another way, right? So there are several other ways. You can do the pairwise classification also. A versus B, B versus C, C versus A, and then you count the votes. Whichever get the maximum vote, because you are doing A versus B. So if B gets the vote, then you are doing B versus C. B gets the vote, the point belongs to class B, and so on, right? The next is text categorization. I mainly took this example because some of you are working in text categorization, right? So if you see there the problem is both features and the data, right? Why? Because how do you make the features? There you see after deleting the stop words, right? You pick up the words and those words becomes your features, right? The property of text categorization, the data property is that it's highly sparse. The word which is present in one document may not present in another document, and so on. So you may have few of ones and remaining as zeros, right? So in this type of a situation where the information is very sparse, will SPM will work? The answer is yes. SPM will still work in this type of a scenario. This is the general way to calculate the phi of xi. As I said, it depends upon the context to context. Whether you are working with text data, whether you are working with medical data, or whether you are working with the image data. The kernel will depend upon the data inclined. This is again the multi-classification I have already discussed with you. This is tree-based classifier. You try to make the tree. So again, the logic is very simple here. Based on the properties of the data, you have A, B, C. You may take A here, calculate B, C, classifier, and then B and C. So if the next pattern comes in, you have a classifier here. If it says it belongs to class A, it belongs to class A. But if it says it belongs to class B and C, you check the classifier here. So whether it belongs to B or whether it belongs to C, the decision would be finalized with the help of this tree. So the advantage of this is very fast, right, compared to the other classification techniques. This is, you take all of them together. The advantages here is this. See, when you are working with three classes, let's say this is the representation of this class, this is the representation of this class, and this is the representation of this class, right? You don't have any rule to classify these points, right? You are unable to get hold of the classes corresponding to these points. In that case, this problem will help you. What it will try to give you a classifier something of this sort, where it will try to bifurcate this into three particular regions. So the classifier would be defined properly in this particular case like this, and so on. So that is the only advantage in this. So if all those doesn't work, that is the pairwise, one versus rest, or the tree, you may go with this class classifier, SPM, taking all the classes together. This is some representation. Then of course that comes what is the classification criteria, how do you check how does one algorithm works better than the other algorithm. So what you do is generally you try to calculate the training accuracy. So basically you try to find out the number of patterns which are correctly classified, which have got their correct labels, divided by the total number of patterns. Right? This is how you get hold of the training accuracy and testing accuracy. This is what they were here. This is true in general for all the data sets, whether it's text data set, whether it's disease data set, cancer data set, everywhere. Right. So these are some references. Any questions? See, as I started with this talk that the main differences between the existing algorithm and this algorithm is that this is a convex Pyramus problem, right? If you know the solution will exist, this will give you a solution, and this will work for usually many of the data sets. For the data sets for which it's not work, you will go with the genetic algorithm. Yeah, exactly, it's followed by the genetic algorithm, but there it's an iterative process. Right? You need to get hold of the information, what sort of a gene to form, what sort of fitness criteria to take, right? Because depending upon the fitness criteria, you will get hold of the classification accuracy by If you select the wrong fitness criteria, your classification accuracy will modify accordingly. But in this case, you don't have such an assumptions, right? And so the only assumption is that the kernel function. The kernel function, they are parameters. And those parameters and kernel function, you will select the 10% of the data set. That data set is part of the whole data set. Whereas in the case of the genetic algorithm, what you do is you try to first find out the genes, right? And then you try to mutate and then you do all those things. That is based on what fitness function. If that fitness function goes wrong, right, then you need to go with another fitness function and so on. That will fit with your data set.
If we go directly this after review P, review I, what will be the
What will be the?
that what will be the code?
You want to say that if you
take same
sort of optimization problem in genetic algorithm.
Ma'am, this is applicable only to supervised learning. This is applicable to only if you have a training set like supervised.
This is workable for supervised, this is workable for semi-supervised, and now we have a clustering algorithm on these framework. So it is workable for unsupervised learning also. I will not discuss those algorithms here, but on these on the line of support vector machines, you have for the regression problem, for the semi-supervised, supervised, and as well as for the classroom.
One question.
Like as you said in beginning, it's a non-fact parameter.
It's a non-parameter. We are not
It is highly dependent on the kernel. So the kernel is one of the most important parameters.
that is not parameter. Parameters, when we say parameter, we are looking to the distribution of the data. So initially we have some information of the data, from which distribution the data is coming from. Because depending upon the data, for example, if you know that the data is coming from a normal distribution, you would like to have your decision surface in that particular form, right? So that is basically the parameters are coming from. The only parameter here, there are two forms of parameters. One is when you represent it with the density information, when you represent it with respect to the probability distribution information and data information. Here I am not giving any parameter with respect to the data. The only parameter which I am going to provide is the kernel. But also providing
Once like you got the
once it is fixed,
like you said, once you have got the separable, like in case of true information linear separation, you don't need any information about the rate. So kernel is like giving a kind of the direction to get your separable. So it's a very important independent data.
yeah. But once it is there, it is fixed. I'm not going to change it. Right? And that selection is made only on the 10% of the data. I'm not looking at the whole data set as such. I'm just looking at 10% of the data. If I will go with the parametric assumption, then I have to see what sort of data I have, from which distribution it is coming from. Right? That is not there. I'm just looking 10% of the data, which is very small as compared to.
Ma'am, I have two questions. So first is there any specific reason to call it a machine?
Machine, yeah, as I said, it's a black box. So for those who are not from the optimization domain, those who don't appreciate the problem as such, the optimization problem as such, for them it's a machine. It's a black box.
And another question is, suppose we are having this one against the rest approach, and a sample gets classified to two classes. So how I should take the decision that which class it should?
It won't be. It will occur only in this type of scenario, you know, where I don't have any information. In this case, only a point will be classified to two classes. Otherwise, it will be classified to just one. Any other questions?
Ma'am, I have a question from initial slide. In t-dimension data, you have selected alpha I. How many alpha I can select, and what is the method of select that alpha I?
You don't have to select alpha I. It will come from the optimization problem, right? Once you solve the optimization problem, you have those alpha I.
Have you said I have selected 3 alpha I?
No, I have not selected. The optimization problem, it gave me the solution. The solution was such that only 3 alpha I's were non-zero. And remaining was 0. So there is no point of selecting, right? I already did from the optimization problem. information in hand, we are going to use whether the linear kernel, a non-linear kernel, or hard mark or soft mark classifier. So you need to first, get hold of the information of the data. You need to have a feel of the data. Without actually feeling what type of data you are dealing with, it's very difficult to use any classifier, whether it's KNN, whether it's K-mean, or whether it's SVM. First know the characteristic of the data. That's the first step you should do. Right? And then only you should decide upon the classifier. Because the classifier is not like magic, which could get in any set of data and give you the solution. It's not the case. For example, I have my personal experience when I was dealing with the financial data. SVM didn't work. Right? No other classifier works. We need to build up yet another classifier for that particular type of data. So that is it.
Could you give the idea like for clustering testing, how to support? Just an idea.
There is a paper, you can get hold of that because see it's lunch time and we are getting late. I need to get hold of the videos. Any other questions? If not then
So she is available outside if you need an
she is an associate professor at Jadavpur University, Kolkata. She earned her PhD degree in computer science from Jadavpur University in 2004. She had got many awards. One of them were SINFA UNESCO India Fellowship in 2002. The same in 1998 also she received Dr. K.S. Krishnan Fellowship as a Senior Research Fellow from the IIT Coimbatore in 1997. She was a co-investigator at the project funded by the Department of IT India from 2002 and 2003. She was the principal investigator of the project funded by AICTC New Delhi from 2002 to 2005. She worked as a coordinator of the project funded by European Union from 2009 to 2013. And she has published 25 journal papers in international reputed journals, 33 conference papers, and co-authored 8 books in the field of swarm intelligence, multi-objective evolutionary algorithms, artificial intelligence. So I invite her to take the dice and would expect the presentation on evolutionary computation and its application. Am I audible? Yes.
Okay. Thank you for the nice introduction. And first of all, I would like to thank the organizer, particularly Mr. Mukti, for giving me the opportunity to deliver this particular talk on evolutionary computation. So, before going into discussing each and every detail, first of all, I would like to inform you that what genetic algorithm is in short. It's nothing but a kind of search algorithm only. Now, what type of search algorithm is it? We know that search can be categorized mainly into two classes. One is blind search or uninformed search, and the other one is informed or heuristic search. Okay. Now, in blind search, we do not have any information regarding the location of the goal or priority of the goal or something like that. Whereas in case of informed search, we have some problem-specific information. Based on this information, we move ahead to get the goal node in reasonable amount of time. So it might so happen that we will be obtaining the near optimal goal, not the best one or the global optimum, if I use certain kinds of information. Okay, so this type of information, whatever we are using, is termed as heuristics also. So this kind of genetic algorithm, evolutionary computation type of search technique, these come under the category of informed search procedure or heuristic search procedure mainly. Okay. Now, one of the striking difference from any search algorithm to this genetic algorithm is that genetic algorithm works with a set of solutions simultaneously, whereas some other typical algorithms normally works with a single solution at a particular time. Okay. So with this very introduction, I would like to go into the detail of this genetic algorithm. Okay. So my talk will the introductory part only, introduction to evolutionary algorithms and its applications. And I would like to mention or highlight some of the areas. I mean, how can we use evolutionary algorithms for these type of problems. In short, I would like to inform these particular things. One is on constraint handling, another one is to solve traveling salesman problem, a combinatorial optimization problem, we all know. The third one is under clustering pattern recognition task, and the fourth one on an image processing task, the how to enhance an image. So what are evolutionary algorithms? This refers to the study of foundations and applications of certain heuristic techniques based on principles of natural evolution. Now, why do we take into consideration the concept of natural evolution for solving any problem? The thing is something like that. Say natural evolution is a black box to me. Now, what we see in nature is that starting from a single cellular creature amoeba, we, the human being, has been evolved. Amoeba is the lowest fit one, okay, most simple. On the contrary, we, the human being, are the highest fitted but most complex. So, starting from our lowest fitted organism, it is with the help of this black box termed as natural evolution, the highest fitted organisms are evolved. So, starting from lower fitted creatures, higher fitted creatures are evolved through the process of natural evolution. So that is why we are taking into consideration some of the operators or procedures of natural evolution for solving our task. So what we will be doing? We will start with some initial set of solutions, and then by learning some of the concepts of natural evolution, this is another black box say. So initially we will have a set of solutions, and then with the help of certain operators, we will try to produce better and better quality solutions. Okay. So at end, whatever we will be obtaining, we will term this as the best solution or near optimal solution or something like that. Normally we cannot say that it will always give me the global optimal solution, because it is a kind of heuristic procedure. Okay. But there is a tendency that starting from weaker solutions, it will generally evolve to better and better quality solutions. So the aim of designing these evolutionary algorithms is to mimic some of the processes which take place in natural evolution in an algorithmic fashion. Okay. There are four major categories under evolutionary algorithm. One, evolutionary computation. The first one, GA, genetic algorithm. Then GP, genetic programming. ES, evolutionary strategy. And EP, evolutionary programming. Now note that all these four typical components which are coming under evolutionary computation, they more or less evolve in different parts of the world in more or less exactly at the same time. Okay, but they named it in a different manner. But there are certain subtle differences among these four techniques. But all these four techniques come under the same framework termed as evolutionary computation. So what we see in evolutionary computation is that the evolution is a process which operates on chromosomes, but not on the organisms itself. It doesn't directly operate on organisms, rather it operates on the encoded version of the organisms termed as chromosomes. Okay. And we see that there is one procedure called natural selection. Due to this natural selection, with the help of this Darwin survival of the fittest strategy, the better and better quality solutions are evolved down over a set of generations. And how do we get the new solutions out of the old ones? there should have been certain operators, mainly recombination and mutation. These two operators are in use for genetic algorithms. Okay. So this is the skeleton of an evolutionary algorithm. We start with an initial population. A population is nothing but a set of solutions. In a such space, if I am in a position to solve a problem, say for example fx equal to x square, where x lies between 0 to 31 and x can take an integer value, then there will be 31 different combinations or options, 31 different answers. But among these set of answers, and 32 different answers, 0 to 31, but among these set of answers, x equal to 31 is the best one. But that we will not be trying to find out using the exhaustive search procedure, rather we will be using some heuristic kind of things. Okay. So in case of initial population, we will have a set of assumed solutions initially. So a set of assumed solutions is termed as a population. So we start with a population at t equal to 0, iteration 0. And until some termination condition is achieved, we follow some of the procedures. What are those? We will evaluate each and every solution of the population by using certain evaluation function. In evolutionary computation framework, we call this as fitness function. Okay. So evaluate PT, then we will have for each and every solution of the population. Now after evaluation, we will have its fitness value. So based on their fitness values and using the diurnal survival of the fittest strategy, we will select some better fitted ones with certain probability. So select, with the help of the select operator, which will be applying on PT, we will obtain a set. Okay, but this P dash T doesn't contain any new solution because I have not used any operators. So only copied version of some of the old ones. Then on these P dash T, reproduction operators will be applied to obtain newer and newer solutions. So P double dash T will come out. Now initially we had the old population PT and the newer one P double dash T. So what to do with these two populations? Should we delete all the old members to replace the new ones? So that comes under replacement strategy. Depending on the replacement strategy, maybe some portion of PT will be replaced by some portions of P double dash T or something like that. So we will get a new set of solutions, P double dash T. Okay. So T equal to T will be implemented by T plus 1, that means the next iteration will again start and the same procedure will continue until the termination condition is achieved. So this is in short the whole genetic algorithm, whole evolutionary computation procedure. I will discuss each and every part of it in more detail. Now as I have mentioned that all the four components of genetic evolutionary computation were evolved in term more or less in the same time, but at different parts of the world. Now, where are the major differences between these four components? The major differences are something like this. Evolutionary programming is closely related to evolutionary strategy, and unlike GA, genetic algorithm, no crossover operator is used in evolutionary strategy or evolutionary programming except recombinative evolutionary EX, recombinative EX. And in GA we notice that crossover and mutation are, these two operators are the primary, crossover is termed as primary operator and mutation is termed as secondary operator. But whereas in EP, only mutation is used. Okay. And mainly ES and EP, in ES and EP more emphasis is placed on behavioral changes rather than on the modification of genetic material. So as a result, it might so happen that the structural part of a chromosome may be different as compared to the genetic algorithm component. So as a result, what could have happened is that the genotype in ES on EP is usually very different, maybe real value vector, ordered list, depending on the problem that I want to solve, and mutation operators are tailored to deal with such types of representations. Okay? So these are in short the differences among the 4 different components of evolutionary computation. Now the question might come that when should we use EA? The example that I have given just now, that try to find out maximize the function f(x) equal to x square, where x lies between 0 to 31 and x can take only integer value. For this simple function, there is no need to use GA, because GA itself is quite complicated. So we will be using GA when and only when we will gain something out of it. Okay. So definitely we will use GA when the search space is quite large. Because if I use any kind of exhaustive search process, if the search space is quite large, then it will take quite a huge amount of time to find out the best solution or global optimal solution. Rather, we could use some kind of heuristic information. So, and GA is one type of heuristic search process. And the search space, we could use evolutionary algorithm where the search space is known not to be perfectly smooth. Because we know that if we try to, I mentioned that evolutionary computation is nothing but a kind of search process. Now it can be used as a kind of optimization technique also, either to find out the maximum of the function or to find out the minimum of the function. Okay. So this can be used as a kind of, as a type of optimization technique. Now, if we want to find out the maximum of a function or minimum of a function, derivative based procedure is sufficient enough to me. There is no need to apply GA, but the major lack of this derivative based procedure is that it will operate if and only if the function is continuous. Whereas even if the function is discontinuous, GA can be applied. Okay. So the search space, we could use GA evolutionary algorithm if the search space is not known to be perfectly smooth. Okay. And we could also apply this type of search procedure where the search space is not unimodal. That means there could have been more than one optima. Okay. And or the search space is not well understood. We could also use GA where the fitness function itself is noisy, because we will see that this type of search procedure is a kind of adaptive search procedure. It tries to adapt the changing environment. So if the environment gets changed, it will change automatically on its own so that it can cope up with the changing situation. Okay. Or we could use evolutionary algorithm when the search time should be minimum. This is the first thing that I had mentioned, because we will apply an evolutionary algorithm when and only when I will gain something. Okay. So if the search time is quite high, then there is no need to apply GA. We could use any kind of enumerative search procedure or something else.
You are using GA and EA?
GA is one kind of EA. Okay. So that's what I mentioned earlier. Could you recall? Sorry. There are 4 components under evolutionary algorithm frameworks. One is genetic algorithm.
Is they applied to GA also?
Yes, the same framework will be applied to GA. These are the major differences among the 4 components. Okay. So my talk will mainly be concentrated on one particular component, and as you can understand that if we modify different things, a little bit modification, we will be obtaining other components also. Okay. In case of normally there is the third component also, genetic programming. Yes, the third component, genetic programming, where the programs are evolved. Here the chromosomes are looking like a program can be represented as a parse tree, as a tree. So in case of GP, the chromosome looks like a tree. So the structure of the chromosome is changing. Whereas in case of GA, a chromosome looks like a linear structure. Okay. So I will concentrate on the, as I mentioned, the one component of it, the genetic algorithm component. It has been developed by John Holland in 1960 and his students, and he got inspired by the the theory of Charles Darwin's theory, and based on this, basically this particular procedure has come up. So if we just start with genetic algorithms, what are genetic algorithms? As I told you that genetic algorithms are adaptive computational procedures. So if the environment gets changed, it will change on its own automatically so that it can cope up with the changing environment. So this is one of the good criteria of any algorithm. Okay. So GAs are adaptive computational procedures modeled on the mechanics of natural genetic systems. Okay. They act as biological metaphor and try to emulate some of the processes observed in natural genetics or natural evolution process. Okay. So we will not consider each and every processes that we found out in nature. Okay. We are taking into some of the processes that are observed in nature. And another aspect, another characteristic of genetic algorithm is that natural evolution operates on encoding of biological entities in the form of a collection of genes termed as chromosomes. So a set of genes is called as chromosomes. Similarly, genetic algorithms will also operate on string representation of possible solutions. So if I again take the same example that maximize fx equal to x square and x lies between 0 to 31. So there are 32 different possible solutions of this function. Among these, x equal to 32 is the best one that I am looking for. Okay. So if I use the same problem and if I say that I have to use genetic algorithm, normally in simple genetic algorithm, the chromosome is encoded as a binary string. So if there are 32 different possible solutions, 5 bits are sufficient for me to encode any solution. Okay. So we will encode each and every chromosome using 5 bits. So this is a string. Okay. So GAs operate on string representation of possible solutions. So maybe 00100 could be one possible solution. And in this particular problem, all ones 11111 is the final answer that I am looking for. Then another one of the other characteristics is the selection process. As I mentioned, that selection obeys the Darwinian survival of the fittest strategy. So here nature, as we see that nature acts as the environment. And in case of genetic algorithm, we will use some function, evaluation function or objective function. So for the evolutionary computation term is used, we call it as fitness function, will play the same role. Then variation could be introduced mainly through genetic operations like crossover and mutation. So where are the similarities of natural evolution and GA terminologies? In natural evolution, we talk about chromosomes, whereas in case of GA, we will call it as, it is viewed as string only. A string is nothing but a chromosome. Then in natural evolution, we talk about gene. In GA, we will call it as feature. Okay. In natural evolution, it is allele, whereas in GA, it is nothing but the feature value. Whether whether the color of the eye is blue or black or something like this. Okay. Genotype is the string structure. 00100 is the genotype. and phenotype is the external behavior, external expression or the decoded structure. Okay. So if we encode, if we decode 00100, we will get certain integer value, and x equal to that or something like this will correspond to the decoded structure. Okay. So these are the major components of genetic algorithm. I'm going to discuss each and every component in more detail. So the first one is population of individuals. So here individual, chromosome, organism, they are more or less synonymous. We can term it in a similar fashion. So what is the population? I mentioned that it's a set of chromosomes which represents the parameter set. So if the functional form that I have mentioned, that try to maximize fx equal to x square. For this function, I have only one feature, one parameter, this is nothing but x. So I have to find out the value of x so that fx gets maximized. Now, fx in fx we have only one parameter. On the contrary, it might be so happen that the functional form is f of x, y, z. So x, y, z, there are three parameters or three features. So in this particular example, we are considering there are p parameters. For each and every parameter, I have to find out the suitable values of it so that the function gets maximized or minimized or something like that. Okay. So in this case, maybe x1 has been encoded into 4-bit binary string, x2 also 4-bit binary string, and then xp also 4-bit binary string. But this is the simplest case. The number of bits that will be required to encode any parameter, it depends on the resolution of that parameter only. Because if I need to maximize fx, where x lies between 0 to 31 and x can take only integer value, I need 5 bits. But where on the contrary, if the function is something like fy and y can take any value between 0 to 15, I do not need 5 bits. Okay? So if the functional form is having f of x and y, x can take values between 0 to 31 and y between 0 to 15, then x will be encoded, definitely be encoded using 5 bits and y using 4 bits. For the same functional form, if x and y can take any real number, then x should be encoded using more than 5 bits and y should be encoded using more than 4 bits. So the number of bits that will be required to represent any parameter depends on the resolution or the range of that parameters only. Okay. So afterwards what we will be doing? So x1 might be encoded using L1 number of bits, x2 using L2 and xp using LP. We will concatenate all these substrings one after another to find out to obtain one particular chromosome. And each chromosome refers to a complete solution of the problem. Okay. So this size of the population, then what will be the size of the population? This size may be kept fixed or may be made variable also. In nature, we notice that it's not a fixed size population, it's a variable size population. But in case of a class, it's always a fixed size population. The student strength is fixed. Okay.
But in nature, it is also fixed.
Nature is at any particular point of time, it's not fixed basically. At time t, maybe there are one in India at time t and at time t plus 1, the number of solutions differ.
In nature, the chromosome is fixed in the body. That is what is I'm saying.
It's not the chromosome. What is the population?
Population number of chromosomes, no?
Number of chromosomes each chromosome refers to a solution.
Yes.
Okay.
Yes.
So in nature, how do you say that the number of chromosomes in a population is fixed? In an organism is fixed,
It's fixed.
but number of organisms is not fixed.
Yes, in an organism it
In
is
an
fixed.
organism it's
Yes,
fixed,
it's
but the
fixed.
number of organisms that exist at any point of time t is not fixed. So that's what I am saying.
But these chromosomes represent the chromosome, the genetic chromosome of the human being.
No.
Yes, solution of the problem. Yes, I am agreeing. These are the solution set. As per my concept, I am just discussing.
You are 100% correct that in an organism the number of chromosomes are
It's
fixed.
fixed.
But
And
whatever I am saying is that I am not talking about a single organism. Okay. In an organism, the length of the solution